of the extension graph as behaving somehow like Dane twists about simple closed curves. And if one can prove a theorem about mapping class groups, one should be able to formulate and prove an analog about right-angled Artin groups using this basic dictionary as a guide. Okay, so let me first observe that the right-angled Artin group acts on the extension graph by graph automorphisms. Just by the natural conjugation action of the group on itself, and the mapping class group acts on the curve graph by graph automorphisms. So we think of both the extension graph and of the curve graph as metric spaces with the graph metric, and then both of these actions are by isometries. So the first result that I'd like to state, so the theorem itself is relating the algebra of right-angled Artin subgroups, of both right-angled Artin groups and of mapping class groups to the extension graph and the curve graph. So this theorem and all the others I'll be stating throughout this talk, unless I know otherwise, are joined with Sang-hyun Kim. So the theorem is there's really two analogous theorems, which are literally the same statement with just replacing extension graph and curve graph in the appropriate statements. So let I be an inclusion of graphs from a finite graph lambda to the extension graph gamma e. Then the map I star n from the right-angled Artin group on lambda to the right-angled Artin group on gamma, given by sending the vertex v to I of v to the nth power, is injective for all n's. And there's a completely analogous statement for right-angled Artin subgroups of mapping class groups. So let I from lambda to the curve graph be an injective map. Then the analogous map I star n from the right-angled group A of lambda to the mapping class group mod S, given by sending the vertex v to twist about I of v taken to the nth power, is injective for all n sufficiently large. And one can actually say a little bit more, give a sort of converse. So for that one, it needs a further definition. So we let x be any graph, and we'll write x of k for the complete graph of x. What I mean by this is the vertices of xk are non-empty complete subgraphs of x, and the edges in xk are given by pairs vk1 and vk2 here K1 and K2 denote complete subgraphs of X, such that K1 and K2 is complete. So note that the clique graph on any graph contains a natural copy of the original graph. So we have a natural injection that way. So now one can state a converse of that first theorem that I have there on the algebra.
Does that just mean that one is included in the other when the union is complete?
Not necessarily. So for example, if VK1 and VK2 corresponded to two vertices themselves, which are themselves complete subgraphs, and if they span an edge, then they are adjacent to the clique graph as well. So the theorem is that suppose that A of lambda sits as a subgroup of A of gamma for two finite graphs lambda and gamma, then there exists an embedding of lambda into the clique graph of the extension graph. And similarly, suppose that A of lambda embeds into the mapping class group mod S. Then there exists an embedding of lambda into the clique graph of the curve graph. So this is not it's not a real converse to the algebraic theorem I gave there, because it's just not. But one can put further conditions to make it a converse. For example, one can show that if gamma is triangle free, so that's equivalent to saying that there's no copy of the free abelian group of rank 3 inside of A of gamma, then we have that A of lambda sits as a subgroup of A of gamma if and only if lambda sits as a subgraph of the extension graph gamma E. In general, the converse that you would want, namely getting rid of this K, is just false. There are counterexamples due to Casals, Ruiz, Duncan, and Kazachkov. Okay, so that's the algebraic perspective of the analogy that I wrote up there on that board. So now I'd like to talk about the geometry. So there's the A of gamma action on the extension graph and on the mapping class group action on C of S. So first, one can say a few things about, one should say a few things about the geometries of these graphs themselves. So Saul mentioned in his talk that, I'll say this as a fact, that the curve graph of a surface, when S is sufficiently complicated, otherwise one has to give an appropriate definition, the curve graph is connected. And infinite diameter. And a theorem of Masur-Minsky, which, as was mentioned as well, has been made much more effective by several authors recently, is that the curve graph is delta hyperbolic. Okay. in the right-angled Artin group case, one can say very similar things. One has to be a little bit careful with the hypotheses. So if you assume that gamma is connected, then the extension graph is connected. If gamma is not a non-trivial join, then gamma E has infinite diameter. So let me just say what this means. So a graph is a non-trivial join. So it's written J1 star J2 for two non-empty subgraphs if every vertex of J1 is adjacent to every vertex of J2. So in other words, you can write the opposite graph. So this is the graph with the opposite edge relation as J1 op is joint union J2 op. Or equivalently, the right-angled Artin group on J is a direct product. So now the analog of the Masur-Minsky theorem is that gamma E is a quasi-tree. This is under the assumption that gamma is connected. So when gamma has finite diameter, which is precisely the case where gamma splits as a non-trivial join, then gamma is a quasi-tree because it's quasi-symmetric to a point, and then otherwise it's an honest uniqueness quasi-tree, and therefore delta hyperbolic.
Can one quantify the quasi the way that it was done for the curve complex?
There's no universal delta that works, so it depends on the diameter of the original graph. In general, you can have loops that are as fat as you want, but in a particular graph, they're never fatter than a certain diameter. Okay, so the central fact about the geometry of these two actions of the right-angled Artin group on the extension graph and of the mapping class on the curve graph is acylindricity. So this is so acylindricity is a notion which is due to Bowditch, which is a weakening of proper discontinuity, which allows for infinite point stabilizers. So the general setup of acylindricity is as follows. So X is going to be a metric space, where G is going to act as a group acting on X by isometries. And the action is acylindrical if for all little r greater than 0, there exists big R and big N such that the size, the number of elements little g in big G, such that, there exists big R and big N such that for all pairs x and y in X, with the distance between X and Y at least big R, the number of elements in the group, which little r quasi-stabilize both x and y, so that's for which the distance between x and gx is less than or equal to r, and the distance between y and gy is less than or equal to r, is less than or equal to n. So so G can have some horrible point stabilizers. It can be infinite. It can be really as bad as you want. But if you have 2 points which are sufficiently far away, then you can only have a uniformly bounded finite number of elements, which move both of them very little. That's what this definition says. Okay, so then the theorem due to Bowditch is that the mapping class group action on the curve graph is acylindrical. And our theorem says that the action of A of gamma on the extension graph is acylindrical. Okay. So what does this give us? So one of the reasons for developing acylindricity is one gets sort of almost for free a version of the Nielsen-Thurston classification. It's intrinsic to the curve graph. So the sort of general theorem that Bowditch proved about acylindricity was as follows. So X is a delta hyperbolic graph. And G is an isometric action, which is acylindrical. Then every non-identity element of big G is either elliptic, which is if and only if its stable translation length is 0, which is if and only if every orbit is bounded. Or it's boxodromic, which is if and only if the translation length is bounded away from 0 by a constant which depends only on delta and the acylindricity constants, which is equivalent to every orbit being unbounded. So so Johanna told us about the classical Nielsen-Thurston classification of mapping classes. So there's the Nielsen-Thurston classification, and then there's the Bowditch style now that we have. So we had finite order mapping classes, and these are elliptic. And we had reducible mapping classes, which are now also elliptic. And we had pseudo-Anosov mapping classes, which are loxodromic. And now, because we have the theorem that's somewhere here, we had that the extension graph is is delta hyperbolic, and also that the action of the right-angled Artin group on the extension graph is acylindrical, we get this sort of elliptic loxodromic dichotomy immediately. So the problem is that we have this abstract characterization in terms of the action on this already rather difficult to understand graph, the extension graph. And whereas, so we have this Nielsen-Thurston classification which gives us nice geometric or topological characterizations of these three types of mapping classes.
Thomas, sorry, I apologize, this is something you're going to say later, but do Bowditch's loxodromics always come with a quasi-axis?
Yeah, they do. Yeah. We get a quasi-axis as well, but I'll possibly get to that. Yeah, I think so. Right. So what we would like is a more intrinsic, in our case, algebraic description of a Nielsen-Thurston classification for elements of the right-angled Artin group. So what we get for free is that we have elliptic elements and we have loxodromic elements. And what one seeks is an algebraic characterization. And one can do that in a fairly, well, we can say what this is in a fairly straightforward manner. So what I'm going to write on the right-hand side here is a theorem. So I'm going to assume that take a non-identity element in A of gamma, which is cyclically reduced. So that means that you're allowed to permute the letters that you use to write G and do any in a cyclic fashion. So you write the word on a circle and then you do any reductions that are possible. And so if you look, then you can look at the support of such an element, which are the vertices or their inverses required to write G. So it's not clear immediately, but this is a well-defined notion. And so then the cyclically reduced non-identity element of the right-angled Artin group is elliptic if and only if the support of G is contained in a join. And loxodromic elements are exactly the ones for which the support is not contained in a join. So I'll note that this coincides with the Bairstock-Charney notion of rank 1 isometries. Okay. So now that we have this sort of easy to state algebraic notion of what reducible and pseudo-analog elements of right-angled Artin groups are, we can say something about subgroups which consist only of loxodromic elements. So as was somewhat alluded to in Johanna's talk, I mean, subgroups of mapping class groups which are purely pseudo-analog are of great interest in not only in mapping class group theory, but in algebraic geometry and in type-polar theory. Now Johanna also studied purely pseudo-analog subgroups which come from embeddings of right-angled Artin groups. And what this what we can show about purely loxodromic subgroups is that they're not very diverse algebraically. So if G is a subgroup of A of gamma, which is purely loxodromic, then G is free. So we're not putting any conditions on G, no finiteness conditions. It's not even necessarily finitely generated. So this can be contrasted with Bowditch's theorem, which says that if you look at finitely presented, one-ended, purely pseudo-anosov subgroups of the mapping class group, they come in finitely many conjugacy classes per isomorphism type. So I'm avoiding stating this theorem in its full precision, so basically it says that if you have one particular isomorphism type of finitely presented one-ended subgroup, and you know that it sits inside of the mapping class group, then there are finitely many copies so that any other copy is conjugate into one of them. Okay. So one more thing I'd like to say about loxodromic elements and subgroups of right-angled Artin groups is to point out a funny relationship between a funny analogous result holds for both mapping class groups and for right-angled Artin groups under certain natural hypotheses. So I believe the following theorem is due to Ivanov. It says if you have a subgroup G, which is normal in mod S, and we'll assume that G is not central and non-trivial, then G contains a pseudo-anosov element. This has a funny consequence, which I believe is also originally due to Ivanov. That's which concerns representations of mapping class groups. And what I mean by representation is just actions on sets. So that if rho is any map from mod S to the automorphism group of some set, so X is just any set, and rho restricted to some non-trivial, non-central normal subgroup, G is injective, then rho is injective. Okay, so that's a funny little fact which has an analog in right-angled Artin group theory. So for right-angled Artin groups, this second theorem, which is a consequence of the first, can't be true as stated, because if you have a right-angled Artin group which splits as a direct product, for instance, then you can look at the two projection maps, And those are injective on certain normal subgroups, namely the two direct factors, and so the projection maps are not injective. But what one can show is that if gamma is not a join, and G is a normal subgroup of A of gamma, which is non-trivial, then G contains the loxodromic element. And this consequence for the representation theory of right-angled Artin groups also holds. So if rho from A of gamma to automorphisms of some set is as rho restricted to G injective, then rho is injective. Okay, so that's all I'll say about loxodromic elements in right-angled Artin groups. If time permits, at the very end, I may talk about quasi-axes and the dynamics on the boundary. But what I'd like to talk about now, or what I promised in the abstract, in the Masur-Minsky style theory. Okay, so an important tool which has been used in several of the talks already, so certainly in Jesse's and in Johanna's, was surface projections, subsurface projections. So what subsurface projections allow us to do is to take curves, so vertices of the curve graph, and subsurfaces x, say subsurface x inside of S, and approximate gamma as a curve or possibly a union of curves on x, so one that most resemble gamma. So then there's some sort of topological surgery argument that one can do, so you get a projection map. So pi sub x, as it's written, and maps the curve graph of S onto simplices. So it's not really a map to the curve graph of x, so I'll just use notation and write it that way. It sends vertices to possibly simplices. And so one would like to have a theory like this if there's really an analogy between curve graphs and extension graphs. One would like to be able to define some sort of projection operator which has nice geometric properties like the bounded geodesic image theorem, which has been alluded to several times. Now the problem in the case of right-angled Artin groups is that there are no natural subsurfaces lying around. What there are, though, are sub-extension graphs in extension graphs. So in order to define subsurface projection or vertex link projection in our definition, let's not have this go out the window. So what one needs to do is have an alternative perspective on how this subsurface projection works. So let's just consider the case where we have S and then gamma sitting inside of S is a simple closed curve. And I'll just, even for simplicity, I'll assume it's non-separating. And then we have this subsurface X sitting inside of S, which is given by cutting open S along gamma. And so one can do a surgery definition of subsurface projection from the curved graph of S to the curved graph of X. But there's another perspective which was explored by Masur and Minsky, which said the following: well, what is the curved graph of X? Well, it's naturally identified with the link of gamma sitting inside the curved graph of S, because these are precisely the curves on S which avoid gamma. And so what one can do then is one can look at gamma sitting as a point somewhere, a vertex of the curved graph, and then maybe we have some other curve, gamma prime, which is really, really far away. And now what we want to do so what subsurface projection is supposed to do is supposed to tell us what curves on X look most like gamma prime. And so if we look at gamma prime from gamma's perspective, the natural thing to consider would be to look at all the geodesic segments lying between gamma and gamma prime. So I'll denote that set by T gamma prime. And then you can look at here the link of gamma, which is this, identified with the curved graph of X. And then one can say, well, what if pi prime of X, pi prime sub X of gamma prime is just T gamma and gamma prime intersect the link of gamma? And what Masur and Minsky proved is that these are coarsely the same. So px is coarsely, pi sub x and pi prime sub x are coarsely the same map. So for more complicated subsurfaces which are not just given by cutting open along the curve, one has to do a little bit more work to define this subsurface projection. But this will be sufficient for our purposes. Okay, so now we're going to start with a graph gamma. And for technical reasons, we're going to assume gamma has no triangles and no squares. So most of the theorems that I'll state here are false if you don't have these two assumptions. So now, if we have a vertex V, V sitting in the vertex set of gamma E, the natural analog of a subsurface will be the link of that vertex. So the link of the vertex V inside of gamma E is the natural analog of a subsurface. Okay, so I'll just remark here that if we assume that So what is this link of a vertex? What does it even look like? So we had a natural topological description of the link of a curve inside of the curve graph. But there's actually a natural identification of the link of a vertex with a sub-extension graph of gamma E. So precisely, the link in the extension graph of V is naturally identified with the link in gamma of V extension graph. And so now what we can do is we can define this projection operator in the same way that Masur-Minsky defined their projection operator pi prime, which, so if we want to apply this to another vertex V prime of the extension graph, this will just be a set of geodesics connecting V and V prime intersected with the link of V. And now, so this definition is we have to say something about it. I mean, a priori, it can be really, really terrible. We can have, I mean, for all we know, this projection is the entire link of V, and so our projection doesn't tell us anything. So a theorem that we can state in this context is that the projection operator pi sub V is coarsely well defined. So in particular, there exists an M which depends only on gamma, such that the diameter inside of the link of V's, inside of the link of V of the projection to V of V prime is at most n. Okay, so now what one can hope for is that
Is the link always connected?
Right, so that's a good point that I was trying to sweep under the rug, but now that you've called me out on it, I'll address that. So, as Saul observed, and whenever the link, whenever gamma is triangle and square free, we have that the link of any vertex is totally disconnected.
Okay, so the diameter is 0.
So that's not if you define the metric correctly. So in this case, we have that. If we look at so now the link in gamma of V is some finite set of vertices, and the right-angled Artin group on the link in gamma of V is some free group Fn. And so the difficulty that arises now in the way we resolve it is the same way that in the torus with one boundary component, there are no pairs of disjoint curves. And so in order to get a connected curve complex, you have to modify your definition of adjacency. So we define the distance between in the extension graph here, so link gamma.
Is the distance in the big graph.
Which big
So
graph?
distance in the link should be distance in the big graph minus the vertex.
You can oftentimes find shortcuts, so that's not a good definition.
Okay.
So the way you define the distance between a vertex and its conjugate v is by defining it to be the star length of g. So what this means is that you write g in some free generating set. I'll just assume that there are two generators, A and B, so maybe A to the n1, B to the m1, and then all the way to A to the nk, B to the mk. And then the star length is just the number of alternations between m's and n's. In the Cayley graph of the free group, this is the same as looking at the distance between, so the star length of an element g, you take the origin, then you take the vertex g, and then you look at how many times you turn to get from the origin to g by straight paths. So then this makes the extension graph of the link an infinite diameter subgraph, and so then that makes this, gives this theorem some content. Okay, so now let me mention Masur-Minsky's bounded geodesic image theorem. So this has been alluded to now in both in Jesse's talk and in Johanna's talk. And what it says is that you have a surface S, and then you have this incompressible essential subsurface X, and then you have gamma inside of C of S, a geodesic. So maybe a geodesic segment, it may be a ray, it may be bi-infinite. And then you assume that that each vertex of gamma intersects X essentially. Then the projection onto X of gamma is universally bounded by constants which only depend on the surface S. And so the well-definedness of the vertex link projection, as I've given it here, that gives you almost, so the work one does to prove that almost gives you the analog of the bounded geodesic image theorem for right-angled Artin groups. And just to state it fully, is that first, if gamma is a geodesic in the extension graph, which avoids the length of v, which is the same as the assumption here that here every vertex in gamma intersect X essentially, then the conclusion is that the projection onto V of gamma is universally bounded. And now extension graphs are somewhat simpler geometrically than curve graphs, and so one can say one further thing which is slightly stronger, is that if X inside of gamma E is connected, and X doesn't intersect the ball of radius 2, the closed ball of radius 2 of V, then the projection onto V of X is universally bounded. Okay, so let me just, in the remaining time, let me explain a little bit the intuition behind the necessity of the hypothesis that the geodesic gamma avoid the length of V. So the idea behind that is as follows. So you have your vertex V, and here's the length of V. And now you have some geodesic gamma, which avoids the length of V. And so the idea is that when you look at gamma from V, then you have to look through some bounded subset of the link. But if you dispense with that assumption, then what you end up getting is you have the geodesic gamma, which hits V, and then generally you can do as sharp of a turn as you want at V and still keep the property that you're a geodesic. And so then distance between this intersection point of the geodesic with the link and this intersection point of the geodesic with the link can be as big as you want. And so then the theorem will fail without that assumption. And I think that's the same picture which holds in the case of the bounded geodesic image theorem for surfaces. So I think I should just stop now, because I don't have time to start something new.
Any questions?
Is there an analog of the Ivanov-Korkmaz-Lowell theorem?
Which one's that?
With that, you know, for big enough surfaces, automorphisms of the curve complex for all elements in the mapping class group?
Oh yeah, that's very much not true for these extension graphs. The extension graphs usually have uncountable automorphism groups. So unfortunately, it's too symmetric. Okay. Some other question.
Yeah. So how much of this can be extended to right angle approximate groups?
That's a good question. I don't know. Not something I've really thought about.
Can you access QI rigidity in this way?
That's the hope.
Okay.
How does the universal bound on the diameter of the projection compare to the size of loops in gamma originally?
I think it may actually be independent. It's the size of the projection. I think it's like very small.
Oh, okay. Okay.
Other questions? Let's thank Thomas again.